Hidden oceans under pressure. How icy moons may be boiling from within. Far beyond the warmth of the sun, the outer solar system appears at first glance to be a graveyard of frozen worlds, silent, cratered, and locked beneath kilometers of solid ice. But that first impression is increasingly misleading. A growing body of research suggests that several icy moons orbiting the giant planets are not inert ice balls at all, but dynamic ocean worlds with active interiors. New theoretical work now proposes something even more dramatic. Under certain conditions, hidden oceans trapped beneath their ice shells may actually begin to boil. Not because they are hot like water on a stove, but because changes in pressure inside these moons can push water to a physical tipping point where ice, liquid, and vapor coexist. If confirmed, this process could fundamentally reshape how we interpret the landscapes of moons, such as Enceladus, Mimas, and Miranda. The key driver behind this hidden activity is tidal heating. Unlike Earth, whose internal heat largely comes from radioactive decay and leftover formation energy, many icy moons are needed by gravity. As they orbit massive planets like Saturn or Uranus, gravitational forces stretch and compress them rhythmically. Neighboring moons can amplify this effect, causing heating to fluctuate over time. When tidal heating intensifies, it can melt portions of the ice shell from below, thinning the crust that separates the surface from the subsurface ocean. When heating declines, the shell thickens again as water refreezes. These cycles may unfold over millions of years. Previously, scientists focused primarily on what happens when ice refreezes. Because ice occupies more volume than liquid water, freezing increases internal pressure and can fracture the surface, potentially explaining long cracks such as the famous tiger stripes on Saturn's moon Enceladus. But the new work turns the problem around and asks the opposite question: what happens when the shell thins instead of thickens? When ice melts into liquid water, it becomes denser. That density change reduces pressure within the moon's interior. On smaller icy bodies, researchers calculate that this pressure drop could be large enough to approach water's triple point, the specific combination of temperature and pressure at which ice, liquid water, and water vapor can exist simultaneously. In practical terms, this means that parts of the buried ocean could begin forming vapor bubbles, even without a large temperature increase. It is not boiling in the everyday sense of roiling, high-temperature turbulence, but rather a thermodynamic shift triggered by decompression. Such vapor formation beneath the ice shell could create buoyant forces, internal stresses, and vertical movement that reshape the overlying crust. This mechanism may help explain some of the most puzzling geological features observed on these moons. Enceladus's fractures, Miranda's towering corona and massive cliffs, and even subtle surface irregularities on Mimas might all be expressions of deep ocean dynamics rather than purely external impacts or ancient tectonic activity. Size appears to be a decisive factor in determining how these processes play out. Smaller moons like Mimas, barely 400 kilometers across, may experience significant pressure changes without immediately cracking their ice shells apart. This means they could host subsurface oceans while still looking geologically quiet on the outside. Mimas, for example, is heavily cratered and often described as resembling the Death Star, yet subtle orbital wobbling hints that liquid water may exist beneath its frozen exterior. In contrast, larger icy moons such as Titania may fracture their shells before pressure drops enough to reach triple point conditions. In those cases, melting and refreezing cycles could still occur, but the surface expression would differ, potentially leading to alternating periods of tectonic disruption and stabilization. The implication is that similar heating mechanisms can produce very different landscapes depending on a moon's size, gravity, and shell thickness. The broader significance of this research extends beyond geology. Subsurface oceans have long been considered prime targets in the search for extraterrestrial life, because liquid water is a fundamental requirement for biology as we understand it. If these oceans are not only present but dynamically evolving, with pressure cycles, phase transitions, and internal circulation, they may offer chemically and physically diverse environments where life could potentially arise. At the same time, decompression-driven vapor formation could influence how material from the ocean reaches the surface, possibly feeding plumes like those observed on Enceladus. In essence, what appears to be a frozen wasteland from orbit may conceal an active, shifting interior governed by the subtle physics of pressure and phase change. Rather than static relics of planetary formation, these icy moons may be complex ocean worlds whose hidden activity continues to sculpt their surfaces and perhaps, just perhaps, sustain environments capable of